Okay, Liv, this is the experiment that we did for working out the mass changes during the fermentation of glucose. We had a conical flask, or what's called a sidearm conical flask. It's just got this little opening on the side there. We had 10% glucose solution. We put 0.7 grams, it was 100 ml of 10% glucose solution. We put 0.7 grams of yeast in there and stoppered it, and then we had just a bit of rubber tubing going into a beaker which had lime water. And what we did was we just measured the mass changes over time. So we just took the measurements over a double period, and then I took some afterwards, and we just noticed that the actual mass went down as the fermentation continued, because fermentation produces CO2. The CO2 bubbled through here, it turned the lime water cloudy, indicating that it was CO2, and we just had a mass change. That's it. Okay, this is a graph showing the actual mass change during fermentation. We've got the time in seconds, so this one was data logged, so it's done over a long period of time. This is seconds, so 20,000 seconds, that's a long time. This is the mass. Now the mass change is not huge, we're only going from 119.5 up here to just over 117.5. But there's a rapid mass change to start with, and that starts tapering off as the ethanol that is produced actually starts killing off the yeast. So the actual amount of CO2 produced, which indicates the amount of fermentation that is occurring, starts tapering off. Okay, here's the setup for the heat of combustion prac. We had a little alcohol burner. Start off with methanol, burnt it, measured the temperature change, then did a different burner with ethanol, did the same thing, and one propanol, did the same thing. We then worked out the heat of combustion of those different alcohols for methanol, ethanol and propanol. So here's the heat of combustion, here's the actual results. Heat of combustion and molecular weight. Now realistically we should have a straight line going straight up, but the value for propanol was low because we had incomplete combustion occurring. So the actual, this is a tin can full of water, the tin can got really sooty around the bottom because we had incomplete combustion, so we had carbon being produced, not just carbon dioxide. Once again, we should have a straight line. We should pretty much have a straight line straight through those dots, and propanol should be up here somewhere. But again, incomplete combustion, so we had much less heat being given off than would normally be the case with full complete combustion. But that's our results. Okay, Liv, here's your other question. Student measured the voltage of the cell. Now this thing, that means you've got a copper electrode in some copper ions, and we've got those double lines means a salt bridge. They've got that dipped into chloride ions, so something like sodium chloride for example, with chlorine gas being bubbled around it, and we've got an inert platinum electrode. And that's shown in this diagram. Here we go, we've got our copper electrode sitting in some copper nitrate, copper sulfate, doesn't really matter what it is as long as it's copper ions. We have our salt bridge. We've got chloride ions in here, so that might be hydrochloric acid, might be sodium chloride, doesn't matter as long as we've got chloride ions. We've got chlorine gas being bubbled over here, and we've got an inert platinum electrode. Now the inert platinum electrode does not do anything other than transfer electrons. Now it says they obtained a value of 1.02 volts with the platinum being positive. Platinum being positive means that the electrons were flowing this direction. Okay. So, write the half equations which occur. Well, this is from the table of standard reduction potentials. The first one we want is the copper one. Now, don't get confused. There are two copper ones. There's a copper one with copper 2 plus, there's a one with a copper 1 plus. Unless you stated otherwise, it's always going to be copper 2 plus. Now, that's 0.4 volts. Now, we know that because the electrons are going from here, the copper's not being the copper is not being reduced, it is being oxidized. So this one has to be written the opposite direction. So we write it like this. We've got copper being oxidized to give electrons, and we have an electrode potential of minus 0.34 volts. It's minus because it is the opposite way. This was 0.34, this is minus 0.34 because we've written it as an oxidation, whereas this one is written as a reduction. So we do it the opposite way around. Okay. The chlorine one is down here. We've got aqueous chlorine, actually beg your pardon, we'll go to here, chlorine gas. and chloride ions. Why did I choose that one? Because it's got 1.36 volts. You'll see in a second. So that one is what is actually happening. Okay, so this is half chlorine gas plus an electron going to give a chloride ion. Now that mirrors this particular half cell in the galvanic cell. This one is written as is with the 1.36 volts. Now if we add those together, we get our 1.02, which is our, here, 1.02 volts. So the question says, write the half reactions which occur as the cell produces electricity. These are those. You can put those together if you wanted to, so you'd have the copper plus chlorine gas going to give copper ions plus two chloride ions. Okay, that would be the overall reaction. Let me know if that doesn't help.